we're given z equals x cubed plus xy squared, where x equals uv cubed and y equals u plus v times e raised to the power of w. We're asked to determine the partial derivative of z with respect to u when u equals 2, v equals -1, and w equals 0. Notice here the given function z is a function of two variables, where x and y are functions of three variables, u, v, and w. And therefore, to find this partial derivative, we'll have to apply the chain rule, which is given here below, where if the given function z is a function of two variables, which are functions of three independent variables, we would use the chain rule to find the partial derivatives given here below. But notice in our notes, the independent variables are s, t, and u, and in our problem, the independent variables are u, v, and w. So let's begin by setting up the chain rule for the partial derivative of z with respect to u. We'd have the partial derivative of z with respect to u is equal to the partial of z with respect to x times the partial of x with respect to u, and then we'd have plus the partial of z with respect to y times the partial of y with respect to u. So we'll first determine this partial derivative, and then evaluate at the given values for u, v, and w. So the partial of z with respect to u is equal to the partial of z with respect to x. So we'll differentiate z with respect to x, treating y as a constant. So we would have 3x squared plus y squared. Again, we're treating y as a constant as we differentiate with respect to x. And then we have times the partial of x with respect to u. So here's x, we differentiate x with respect to u, treating v as a constant, and therefore we just have v cubed. And then we have plus the partial of z with respect to y. So we differentiate z with respect to y, treating x as a constant, and therefore the derivative would just be 2xy. And then finally we have times the partial of y with respect to u. So differentiating y with respect to u, we treat both v and w as constants, and therefore the partial derivative is just 1. Now from here, if we were asked to give the partial of z with respect to u, we would want this function in terms of just u, v, and w. But for this question, because we're just evaluating it at u, v, and w, instead of performing substitutions for x and y, let's go ahead and leave it in this form. And what we'll do is determine the value of x and y when u equals 2, v equals -1, and w equals 0. That'll make the substitution a lot more manageable. So let's find x of 2, -1, 0, meaning the value of x when u equals 2, v equals -1, and w equals 0. So here's x, so we have u, which is 2, times v cubed, which would be -1 cubed, which would just be -2. Now let's find y of 2, -1, 0. So y is equal to u plus v times e to the w. So we'd have 2 plus -1 times e raised to the power of 0. E to the 0 is 1, so we just have 2 plus -1, which equals 1. So now we'll determine the value of the partial derivative. Again, when u equals 2, v equals -1, and w equals 0. So we have 3, and then for x squared, we know x is going to be -2, so we have -2 squared plus y squared, which would be 1 squared. So we have this quantity times v cubed, where we know v is -1, so times -1 cubed, and then plus, well, 2xy times 1 is just 2xy, so we have 2 times x, which would be -2, times y, which would be +1. So let's go ahead and simplify. Working inside the parentheses here, -2 squared is 4, 4 times 3 is 12, 12 plus 1 squared, that'd be 12 plus 1 or 13. And we have -1 cubed, that's just going to be -1. And we have plus 2 times -2 times 1 is -4. So we have -13 plus -4, which equals -17. So we now know that the partial derivative of z with respect to u is equal to -17 when u equals 2, v equals -1, and w equals 0. I hope you found this helpful.